So let's look at an example of using the limit definition of the definite integral. And we're going to use right-hand endpoints. So I just created one very similar to the ones you're doing in the homework. This is the definite integral from 2 to 5 of the function 3x squared plus 5. Okay. Now some of you again know already how to use the fundamental theorem of calculus to do this problem, but that is not the way that you should show support here. You can certainly check and confirm as we learn that method shortly, but right now we're going to indeed do the algebra, do the work, which is basically, again, just approximating this function, the area, either under the curve as positive area above the x-axis or negative area below the x-axis. We're going to do that with rectangles, right? N equally spaced rectangles over the interval from 2 to 5. And that's the R sub n, basically. And then we're going to push the limit as n goes to infinity. That's all the limit definition really is doing for this definite integral. So we're going from a lower limit of 2 to an upper limit of 5. The width of each interval, delta x, is going to be b minus a, the length of that interval from 2 to 5, which is 5 minus 2 is 3, over the number of subintervals, which is arbitrary, right, number n. So 3 over n is the width of each subinterval. The right-hand endpoints will be a plus I delta x. All right, so when I is 1, we're going to get a, which is 2, of course, here, plus 1 delta x would give us that right-hand endpoint for the first interval, plus 2 delta x will give us that second interval right-hand endpoint, and so on all the way through as I goes from 1 to n. So this is the expression we need. So here is the limit definition then for this definite integral. It's the limit as n goes to infinity, because that's indeed what we're going to do once we find, this right here is essentially the R sub n that we've been using before we learned about this definite integral and this limit definition. That's exactly what it is, right? You're just summing from I equal 1 to n the area of each of those rectangles, which is what? Width delta x, height f of ci. The function f of x in this case, right, is the integrand that we have. We call that the integrand, what we're integrating, 3x squared plus 5. And so I'm going to evaluate that at 2 plus 3i over n. So notice my equal sign. These are useful, right? Use equal signs when things are equal. So this definite integral is equal to this expression. And notice I start with the limit. So I carry that limit each time until I evaluate the limit at the end. So equals the limit as n goes to infinity, summation I equal 1 to n. And then plugging into the function, right? 3 times what? X, which is 2i plus 3, 2 plus 3i over n squared, plus the 5. Okay, that's the f of ci, right? The f of ci part is right here in the hard brackets, and then our delta x. Don't forget that. Sometimes that gets left off, and that's going to mess you up if you forget that delta x. Okay, you're not going to get a correct result if you leave that delta x off. Okay, so now we've got algebra to do, all right, and before we use our linearity properties for sums and then the power sum formulas. So first thing I do is I square 2 plus 3i over n. So be careful how to do that. All right, remember the idea that a plus b squared is a squared plus 2ab plus b squared. So be real careful. It's not just simply a squared plus b squared, which is a lot of students will do. That's bad algebra. So a is 2 squared is 4. AB is 2 times 3i over n is 6i over n times 2 is 12i over n. That gives me that 2ab. And then plus b squared is 9i squared over n squared, right? So that's just squaring that out. If you want to rewrite it and FOIL it out, first, outer, inner, last, whatever you do, please make sure you correctly do this algebra. Now I have the 3 times all this, so I need to distribute the 3 through 3 times 4 is 12, 3 times 12i over n is 36i over n, and 3 times 9, 27i squared over n squared. Okay. Don't forget this delta x here is still here, 3 over n. I need to finally, I'm going to go ahead and distribute that through. So I've distributed the 3 through here. Oh, and I forgot my plus 5. I forgot my plus 5. So here's a good note, and someone mentioned this. There are easy ways to make mistakes just in this process, not even copying down things, right? Like I've done here. And so what I would say to that is you just do need to be careful, and you do need to show every step in the process. Okay. Now, because I've left out the plus 5 here, I've went through and done everything. My final answer is going to be off. Okay. So here's a couple things. Once we do learn how to use the fundamental theorem of calculus, part 1, and we're able to evaluate these definite integrals a little bit quicker, you'll be able to know the answer to this problem. And so you can verify, at least when you get down to the bottom, that you got the right answer, hopefully, right? If it's not the right answer, then you want to go back through and look and see where you made a mistake. Like here I say, oh, I forgot the plus 5 here. I distributed this out, distributed this 3 out, but I forgot the plus 5. Okay. Now, the thing is, even if you aren't able to catch your mistake, I mean, I hope you're able to on a test or something, by showing your work very neatly and clearly, I can give you, partial credit for most of this. If you just miss this plus 5, you might miss just a point or two, as opposed to all the points on the so on the problem. So please make sure you do that. So this is just me showing you that I am no better than any of you when it comes to doing algebra and arithmetic. I make mistakes all the time. Guaranteed in this process, I'm going to make a mistake almost every time, it seems like. So I'm careful, and I recheck, and anytime I have a chance to make sure my answer seems reasonable, I do that. Okay, so what does this mean here? I'd forgot my plus 5, so when I distributed the 3 over n, I had the 36 over n here, but I'm missing what? Plus 5 times 3 over n, I'm missing a 15 over n, adding that in to there. So that's something I want to include. And now what I've done here is I've broken up this sum by the linearity rules. So I'm going to write this as the sum I equal 1 to n of 36 over n plus the sum I equal 1 to n 108 I over n squared. Now what I've done with the 108 over n squared, since that's a constant multiple, I pulled that out, right? Pulled that out. That's also a linearity rule. You can pull constants out. So remember, the linearity rules say that the summation of AI plus BI is the summation AI plus summation BI, and it also says the summation of a constant times AI is the constant times the summation AI. So that's the, that's the two basic linearity rules that we have there. Okay, so and then I've got the summation 81i squared over n cubed, right? Which I pulled the 81 over n cubed out. And now, because I forgot my plus 15 over n, I'm going to add in, right? Plus summation I equal 1 to n of 15 over n. Okay. Now I'm going to evaluate these things. So first of all, this first one, I equal 1 to n of a constant, 36 over n, right? So I'm going to make use of the following, and that is that the summation again of I equal 1 to n of any constant, right, is equal to just the constant times n, right, or n times the constant, because this is just, I equal 1 to n of a constant is just the constant plus itself n times, so it's n times the constant. So this will be 36 over n is the constant, right? It's constant because there's no, n is a variable. You think, hey, isn't that a variable? But the variable in this summation is I, right? I is changing from 1 to n. So n we're thinking is for fixed n, we can evaluate this expression. So 36 over n is a constant times n. Of course, we know what's going to happen there. 36 over n times n is going to give me 36, right? Then what about this? 1 over 8n squared times this? Well, there's where we're going to use the power sum formulas. Again, you're going to be given the power sum formula, so you're going to be given this one here. I equal 1 to n, so 1 plus 2 plus 3 all the way to n is equal to what? This expression. or this expression. You can use either one. I prefer this latter one, and that's what I've done here. I've replaced that summation with the power sum formula. And then 81 over n cubed times all of that, right? I squared is this stuff here at the end. That's what I'm going to use. So again, these three formulas will be given on the test. And notice I also probably will give you the limit definition on the test as well, which is what we started with. Okay, so most of you will have it down by the time we get to test time, but I will include that as a reminder as well on the test. Okay, so the only other thing I forgot, again, I forgot my little thing here. So what is that going to add to this? It's going to add, since it's a constant again, it is the constant 15 over n times n. Let me tell you one thing about, I missed this 5 from the very beginning, remember? Carried it, I forgot to carry it down. If I remember to do it, what I would have done first here before distributing the 3 over n, I would have went ahead and done 12 plus 5 is 17, right? And so I would have 17 times 3, which is what, 51. 17 times 3 is 51 over n. 51 over n. That's exactly what 36 over n plus 15 over n is, right? 51 over n. So I would have 51 over n, 51 over n times n. I'd have 51 here. Okay. Whereas over here, when I do 15 over n times n, I'm going to add in what? Add in 15. But of course, 15 plus 36 again is 51. So that, I would rather combine it up here. Had I done it, had I not messed up, I would have combined it correctly here and then continued on. So in other words, I would combine any like terms in here, before going down and proceeding. Okay. Now, so again, 36 over n times n is 36. And then I distribute this through, right? 108 over n squared. 108 over n squared times n squared over 2. 2 goes in 108 54 times. N squared divided by n squared is 1, so I just get 54. When I multiply it by here, 2 goes into 108 54 times. I've got n divided by n squared. N divided by n squared leaves me 1n in the denominator. And then here I distribute the 81 over n cubed through. 3 goes into 81 27 times. N cubed divided by n cubed is 1. And then here 2 does not divide evenly into 81, so I get 81 halves. N squared divided by n cubed, I've got an n in the denominator. And then here n divided by n cubed leaves an n squared. 81 sixths, if I divide top and bottom by 3, I get 27 halves. So you're just simplifying that expression. Plus what? 15 over n times n, the thing I forgot, plus 15. Okay. Whew. All right. So again, just illustrating, you need to be careful. You need to work through these problems because number one, familiarity, it's like doing exercises, your muscle memory, right? You do things to work out. First time you try and do a particular movement, you're like, wow, that really feels weird. Can't really get that down. But after a while, it becomes easier, but you've got to practice. So you've got to practice these things. And these are some of the most tedious problems that we do in the course in a sense, because there's a lot of, keeping track of things. Okay. It's algebraically intense. And sometimes you have problems that are that way. All right. In fact, as we've been saying over and over again, and we'll continue to say in calculus, 80 to 90% of what we're doing is just pre-calculus stuff, algebra, trigonometry, basic arithmetic, even simplifications. All right. So now we're ready to take the limit. As n goes to infinity, what do we know about 54 divided by n? Well, that's clearly going to go to 0. What do we know about 81 divided by 2n? That's going to go to 0 because, again, as n gets bigger and bigger, 81 is divided by a bigger and bigger quantity, right? And that overall is going to go to 0. Same thing here, 27 divided by a bigger and bigger quantity is going to 0. And basically, we just have all these constants, right? So that we're going to get 36 plus 54 plus 27 plus 15, right? And so if we do that, I would add them in my head, but seeing as I've already made one mistake, I'll probably do that again. So, you have your technology, you can help do some arithmetic. A lot of you are able to do this in your head as well. But the key is, again, showing your work. Okay, showing your work. So in other words, in homework and on the test, when I ask you to do this problem, you can't simply, start, say here, write this down, after the first step, and then all of a sudden, give me this down here. Okay, that's too big of a jump. You need to show some intermediate steps. Okay, you need to show how you get from point A to point B. Okay, and I know as you're doing this work, it's easy to use lots of resources where you can get the answer with all the work shown and everything. I hope that's beneficial at sometimes to help you see things, but you've really got to do the work yourself. You've really got to struggle through this. So please, I encourage you to do so. And if you have questions about any of these type of problems, please let me know. Hopefully this helps with this one.